The Immersive Digital Experiences Alliance is a non-profit industry association developing a family of royalty-free technical specifications to enable the digital future. Our members bring world-class experience in light field and holographic imaging, distribution networks, and content creation. You can learn more at immersivealliance.org. The IDEA Specialized Contract track consists of 8 segments covering all aspects of immersive media. In this segment, we'll be explaining ITMF, the Immersive Technology Media Format, a new specification enabling interoperability for the next generation of volumetric and light field media.
Hello everybody, welcome to this IDEA content track session, understanding the ITMF specifications. My name is Thomas Alder. I am a software engineer at Otoy, and I work within IDEA and help out on the specifications for the Immersive Technologies Media Format, or ITMF. And in this session, we'll be kind of going through what a scene and a scene description is for immersive experiences, what ITMF is, how it's designed, just breaking down the specs overall. And we'll kind of see how ITMF is different to other types of scene description formats out there today, such as GLTF and USD, to name a couple. Then we'll preview the next iteration of the specifications. Thank you everybody for coming out and checking out this session. I'm hoping that after this you will have a better understanding of what ITMF is, what the media format is, and just how we envision it to be within IDEA. So that being said, why don't we just jump right into the presentation, and thank you again for checking this out. So before we dive into ITMF, let's see what a media format like this can really create. Here are a series of renders that we've done in IDEA using ITMF and Octane Renderer. With these scenes, we look to create an environment that was both photorealistic and convincing to somebody who might be experiencing these type of scenes. These are all assembled into the ITMF container with 3D assets like FBX and OBJ models, those textures, materials, and shaders described in the scene graph. And from this we can see that a scene is the centerpiece of the immersive experience. With these renders we can start to see a metric for good immersive experiences to be the environment and the surroundings of the user. The scene is what the user sees, hears, and interacts with, and the scene is described in a media format called a scene graph or a scene description. This format is not only described, but it may also store the objects that encompass the 3D user is experiencing. Within IDEA, we have defined an ideal scene graph to contain many different objects or nodes, such as one or more virtual cameras, geometric objects which can be textured, materialed, or shaded, lighting, volumes, and audio, all of which may be animated. The scene description media format may also consider interactivity, streaming, compression, extension, and/or a rendering interface within their design. And this is where ITMF steps in. We envision ITMF to be our representation of a scene based on the media format developed at Otoy called Orbix. Our goal is to provide end-to-end support for immersive media content creation, packaging, and network transmission. The current version of the ITMF specs are 1.0, but this enables the packaging and creation of 3D synthetic scenes assembled in digital content creation tools. IDEA envisions the use of the ITMF suite to be both a mastering and distribution format for immersive, interactive media for displays in use today and emerging advanced imaging displays. The suite contains of 3 things. It contains a scene graph, a container, and a data encoding specification. Let's begin by first looking at the basic components of the scene graph. The ITMF scene graph component of the specifications is a node-based scene graph that describes logical, temporal, and spatial relations between visual objects in a scene. Each node has input and output pins that ultimately lead to a render target, providing an interface for the final visual output during serialization. It is encoded using the human-readable XML. And finally, with Lua scripted node graphs functionality, it's extensible with Lua scripts that can also interact with C or C++ code, for example, with the foreign function interface or FFI that is built in. With an IDEA, we're looking at streaming and applying contemporary compression techniques as well. So here's a very basic object or node model of the scene graph using nodes that we introduced before. From this, we can see that there's a direct flow towards the render target. And the render target itself describes parameters for the rendering engine to base what the final output looks like. Things like the number of samples used while path tracing or different types of rendering techniques. ITF has many camera types, including a thin lens camera representing a basic camera, a panoramic camera enabling such things like a cube map camera projection, a baking camera, and cameras driven by the open shading language or OSL. Geometric objects can also have light emissive qualities, and the environmental light can be defined as daylight, texture, or planetary environments. New in the next version will be spectron nodes, which allow for procedural volumetric lighting such as a spotlight. It too can support geometric formats and other scene descriptions such as OBJ, FBX, Alembic, and GLTF with USD in progress. There are placed around a scene using the placement node, for example, or the scatter node, which allows for instancing of the geometry as well. And geometry can also be placed in geometric groupings. Procedural image base and geometric textures that may go operations or mappings can be applied to physically based or non-physically based materials, including diffuse, glossy, metallic, specular, or tuned materials. In the next version, materials will also have the ability to be mixed together or layered on top of one of each other. And with this, you can create a lot of cool different type of effects on geometry with these materials. Shaders defined with the open shading language can also be applied to textures or cameras. Volumetrics can also be defined as part of the scene's geometry. The open VDB format is supported along with mediums that can be associated with the materials of closed watertight meshes, and these can describe the scattering or absorption of light rays within the object's volume. And these mediums can also be applied to the environment's lighting to accomplish things like atmospheric fog, for example. In addition to define the rendering of the scene, such as different types of settings, such as the film settings, animation, render kernel, which enables path tracing or direct lighting rendering methods, for example, render layers and render passes can be defined. Tone app settings can also be defined, such as imaging parameters like the exposure and saturation, denoising, as well as post-processing, such as like the glare that some lighting may come off, emit, or the bloom can be defined as well in these settings. Spatial and immersive audio is also being currently worked on within IDEA. So all these nodes are described in an XML document that too describes the connections between them. But this document and all of the object data is stored ultimately in the container. The ITMF container defines a packaging format that encases the scene's assets through representation as a virtual disk system and the scene graph as the XML file. The container uses binary markup language, BML, defined in the specifications, which is designed to be machine readable and compact for a simple data layer for structured encoded data. The container is made up of ITMF logical units that may be compressed or encrypted, and there are two orderings of the logical units. We'll see in the next slide, streams at the start and streams at the end. On the left are all the logical units in the order for a streams at start encoding method. The ITMF header contains information to identify the container. This is then followed by the stream of data, which is divided into chunks, each with a header indicating parameters followed by a variable length containing the stored data. Optionally, the properties are encoded next with the key value properties of the container encoded. Stream headers describe the data stream. The index optionally follows, which allows random access, providing the start location for each chunk within the container. The directory then provides a list of files and their properties that are within the stream. Finally, the signature and the ITMF footer pairing closes out the encoding. This signature allows the container to be signed cryptographically, and the footer identifies the container and the end of the file. The streams at the end encoding order and makeup, as seen on the right, differs slightly from the streams at start, but enables streaming of data in real time by having the chunks containing the data at the end of the file. The ITMF header is immediately followed by the stream header chunk. The index may follow before the directory, and finally the stream follows containing the data. This best fits the use case of live streaming or media and application-aware distribution, and to this it does not have a footer. So that is the basics of the container. For a greater in-depth look and to see the fields that describe each of these logical units, I encourage you to check out the specification. And this brings us to the final part of the specification suite, which is integral to encoding the scene graph for storage in the container, the data encoding specification. The exact code points required to encode and decode the individual nodes, attributes, and pins are defined in the ITMF data encoding specification. This enables a package to become transportable by providing exact node and pin codings using the scene graph for readability in renderers, digital content creation tools, and display technology systems. So that is ITMF. But even still, we get questions a lot about how does this scene graph differ from other formats, which is a good and fair question. Due to this, IDEA decided to recently release a white paper titled An Overview of Scene Description Formats, which provides a high-level information and comparison of FBX, Alembic, Universal Scene Description, GLTF, and ITMF, which we hope allows people to understand where ITMF fits in this altogether. I encourage everybody to definitely go check out the white paper to see and gain a better understanding of this as well. We find that scene descriptions often have two goals in mind: interoperability and interchange between digital content creation tools and transmission over the network or just to an end user. From the paper itself, we find the main purpose of scene descriptions to be the following, and by looking at each of these purposes, we can quickly see how the scene descriptions differ and provide functionality based on different workflows, content types, and end use cases. FBX provides interoperability between digital content creation tools, asset storage, animation processing, and general packaging. If you've used any type of content creation tools, you've probably used FBX before. It's widespread in use. In Alembic, interchangeability and geometry caching for distilled scenes. And by distilled, it basically bakes out all of the really tough computation networks that a mesh might have and just takes out those rigs and makes it time-sampled animations. USD provides non-destructive composition of files for collaboration earlier throughout the content creation pipeline. Referencing is huge in USD. It allows a lot of artists to work on the same scene at the same time rather than waiting later in the content pipeline. GLTF minimizes asset sizes and runtime processing in the last mile of 3D mesh publication and delivery. The assets are very close to what GPU draw calls require, so that asset size is ultimately minimized to what is needed by the GPU itself, and that's really powerful in the last mile of mesh publication. And finally, ITMF provides end-to-end support for immersive media content creation, packaging, and network transmission. So basically, ITMF provides an umbrella for these scene description formats while providing a rich material system, shading options, and additional assets such as procedural primitives and volumetric lighting to produce scenes that we saw at the beginning of this presentation. But what's next for ITMF? The new version out now is 1.0, but we're working towards a new version which will include layered and hair materials, spectron and vectron nodes, which are basically procedural lighting and geometry, a universal camera, subsurface scattering mediums, geometric and light primitives, and USD Hydra integration as a scene delegate so that many rendered delegates can use the information from the scene to render the same scene. So this has been a walkthrough of the Immersive Technologies media format. If you're interested in the media format or have any questions, I encourage you to get in contact with myself or the IDEA Commons email, or better yet, join IDEA and have direct contributions to the work we're doing. We have seen what ITMF is, and I hope you guys get a better understanding because of it. And thanks for tuning in, and enjoy the rest of the SMPTE conference.
Thanks for joining us in this segment from the Immersive Digital Experiences Alliance. IDEA is a nonprofit industry group developing a family of royalty-free technical specifications to enable the digital future. You can learn more at immersivealliance.org. You can join IDEA, download the ITMF specifications or white paper, or just join our mailing list to stay informed. Thanks for joining us today.